Okay, so the first talk of the session will be given by Qingshan Wang on networks of coupled phase oscillators as a neuromorphic platform trained with equilibrium propagation. So, thank you.
Hello. First, thanks very much for the introduction, and hello everyone. I'm Qingshan, and currently I'm the PhD student in Max Planck Institute for the Science of Light. And currently I'm working with Florian and Clara, and today I'm going to talk about my results on this topic, network of coupled phase oscillator as a neuromorphic platform trained with equilibrium propagation. And so, at first, we are very familiar with the story of neuromorphic computing. Because of energy cost and for known and bottleneck, we may need something to do neuromorphic computing. And one of the ideas to do neuromorphic computing is to use the physical system as a computing platform. And it is, sorry. Yes. And the idea is like in the physical system, one takes some of the nodes at the input, and it may be fixed or maybe influenced by something, and at some configuration, the state of some other nodes are taken as an output. However, in such a physical system, there's a very big problem. It's about the training, because in the conventional digital neural network, the information flow is single directional, which means that we can train the system by directly do backpropagation on it. However, in the physical neural network, then the flow of information is bidirectional. And doing something like backpropagation is very tricky and consumes a lot of source of computation. And in this case, we may ask the question, is there a more efficient method to train such a system? A lot of work has been proposed on this issue, and we can have a look at this review to know roughly about all of the methods. However, in our case, the question is that we want a physical method so that we can get a parameter gradient with physical measurements and just simple calculation. And this sort of method includes equilibrium propagation, Hamiltonian backpropagation, and quantum equilibrium propagation, and so on. And one can also have a look at the review about the detailed information about them. And in our case, the method we use is the equilibrium propagation. This method is used for energy-based model. It is that assume that we have some physical model with some degree of freedom, and on which we have a energy function E, which is in this case called the internal energy. And we also assume that a part of this physical system is coupled to something outside, such as the environment or some other system, which works as the cost function in the supervised learning, and it is called the external system. And we add them together, then we get the total energy. And how do we do computation? We search for the steady states such that the system is stable at that configuration, and we read out states of the output as the output of the network. And in this setting, the equilibrium propagation consisting of two phases. In phase one, we fix the input and thermalize the rest of the network, and then we read the output, and this state is called the free equilibrium. And in phase two, we switch on the interaction to the environment or to another system, which works as a cost function, and then the system is nudged a little bit and thermalized to a new steady state, which is called the nudged equilibrium. And by the theory of equilibrium propagation, one can say that the parameter of the gradients can be obtained by taking the difference between these two equilibriums. And in our case, we're focusing on the system of coupled limit cycle oscillator, this idea originally comes from an optical limit cycle, and we can also couple them together. And such system can be also implemented with superconducting circuits, with exciting polarity system, or with coupled laser arrays, or just with mechanical oscillators. And the system And when a system is perfectly synchronized, its dynamics can be described as a Kuromoto model. And then by rotating the frame of reference along time, one can just eliminate the intrinsic frequency, and one can find that the dynamic equation just looks like the gradient of some energy function. And in this case, we correlate the Kuromoto model to the XY model, and we also relate the coupled oscillators to the coupled classical spin systems. And in this case, we also assume that we fix the phase of some nodes and take that as an input and read out the phases of some nodes at the equilibrium as the output. And the first task we train this is on XOR. We take this to be the cost function because the conventional cost function defined below as D actually converges very slow for XOR, but its performance is acceptable for some other tasks. And the result can be seen in this paper. And we train the system by solving the ODE. Well, we get the equilibrium by solving the ODE. And according to the result, which shows the mean training cost averaged over 1,000 different cases of different initial couplings, the result shows that, okay, in this case, our system can learn XOR, which is taken as the simplest nonlinear tasks. And when training the system, one is met with another problem, which is the dynamical stability. It is that when the system is big enough and complex enough, it may have more than one stable steady state. However, during the training, we also met with this problem, and we finally found that the model stability can be resolved by running the system for multiple times and taking the average with random initial configuration on the systems. And after training, we can still find that even though the steady state on the hidden state shows that after training, the system still have multi-stability. However, at the output node, the results are correct and unique. And after showing the validity of the system on the coupled oscillators, we then turn to another questions. Because in the previous paper, we always stick to the all-to-all connectivity or densely connected layer network. However, this sort of network are not feasible in experiments. So we ask the questions: what is the performance of network of sparse architecture? And we have this paper. In this paper, we focus on different architecture of lattices, and we define different. And we named the simplest square lattice as SQ, and then I add diagonals on it, and we add skip connection on it, and we add both the skip connection and the diagonal connection on it. And we begin the study with it also with XOR. We space the input and the output with some distance so that there are no direct connection between them. And we flip one of the input and see how the output responds to this flip. And the result is very interesting. We found that for the simple square lattice, during the training, the lattice nearly have no response to this flip. However, for lattices of more couplings of higher connectivities, they show some response to this flip, and this response grows stronger when the training is done. And what is more interesting is that one can see that for an SQ, the network first stretch out to look for some correlation to the output, and then once the response is it's cut off other redundant connections. And one can also see the similar things on the evolution of the couplings. we can see that for the simple square lattice, nothing is changed, but for the Florian XQ, the coupling within certain region is significantly strengthened. And then we turn to another, and then we study the effect of skip connections and sites. We train the system on areas and with two architectures. And in one case, we put all the input together, and in the second case, we separate it with one node. And we found that in both of these cases, the network can learn the result very well when the network is shallow, and if the depth grows up, they all have poor performance. And this diagram shows that if the point is falls in the region of the same color, then it is correctly classified. And the overall performance is shown in these two figures. From this, we can see that the success decays as the network becomes deeper, and we mean to improve the performance, we may also need some mechanism like resonating deep neural networks. And what is interesting is that for P3XQ and Florian XQ, the performance is comparable to that of the dense layer network with the same size. And finally, we assess the stacked lattices and test its performance on full-size MNIST. And we define three types of architecture: the LCL, which means that in one layer, one of the nodes is just coupled locally to some other nodes, and thin and like, which is LCL, but with weight sharing and more channel. And the last one is the network of the simplest architecture. It's just the densely coupled layers. And the result is shown in this picture, and we found that the LCL and the thin and like networks all outperforms the deep layer network when one have the same number of tunable parameters. And for LCL and CNN, it can have a 96% of accuracy, and for CNN, which 5 and 10 channels, it can even approach 98% accuracy. So, as a conclusion, we investigated a couple of phase oscillators as the neuromorphic computer platforms, and we proved that the equilibrium propagation works on such a system, and the problem of multiplicity can be overcome via random initialization. And in the second paper, we analyzed various architecture and see their performance, and we found that the networks of sparse connectivity still show very nice expressivity. And in this topic, there is still a lot of questions we can ask about. What about effect of noise? Because up to now, all our works are on deterministic dynamics. And what if you have some other architectures? Can we have better result than this? These also questions. And we can also currently we have already extend the method of equilibrium propagation to quantum systems, and we are thinking of if we implement this on the physical platforms and prepare the ground states with concrete physical methods, such as we do adiabatic evolution on readable atoms, what would be the effect of imperfect ground states? And we have some early result, and it is shown in my poster on the ground floor. And we can know the result by have a look at the three papers, and this is the package I built up to do equilibrium propagation, and it is on the GitHub. Thank you very much.
Thank you for the nice talk, Qingshan. Questions?
Very nice talk. So I have a question. When you simulate your oscillators, do you assume their frequency are the same, or they have some random disorder there?
the basic assumption is that they are perfectly synchronized. So when they are synchronized, they actually oscillate with the same frequency, and we can assume that after moving the frame of reference, this frequency is just taken as 0.
Okay, thank you.
Thank you for the nice talk. I have actually a follow-up question on this. So if the frequency are not the same, right, then you basically don't have an energy anymore. Have you looked into like you know, how good is the gradient estimation still if you, let's say, have small divergence from the exact same frequency across all oscillators?
Actually, if there dispersion in the frequency and if the coupling is strong enough, the system will still synchronize and have a single frequency. However, the problem is that the output may be unstable, and as remember we don't take this as a topic to discuss in our paper, but as I know, in the group of Julie Clara, they have a paper discussing on this issue.
Okay, thank you.
Okay, so if the next speaker could already set up, Sam. Yeah, perfect. We would have, and in the meantime, we can take one more quick question. Otherwise, we can also thank Qingshan again. And
Thank you very much.